Hello, everybody. I'm going to solve question 40, question 45, and question 48 in algebra section for the course Maths1151 at UNSW. These are the questions about the determinants. We are going to practice the concept of determinant. Now, we would like to, for this question, it is a hard question. As you know, the hard questions are unlikely to ask. Yeah, let's have a look how we solve this one. And this seems to me is not a difficult one at all. After all, could be asked. If the determinant is, so this is the matrix that we would like to calculate the determinant, and we would like to prove that this is A times B times C. If you do the row operations, because we have lots of ones here, we can make 0, 0, 0 of these ones. If we do that, this one minus this one, so this way I will have 0 here, I will have A here, I will have 0 here, I will have 0 in this position. And similarly, I will have 0 here, I will have 0 here, I will have B, and I will have 0. I'm taking this row minus this row plus this one. So that will be 0. That's minus plus 0, minus plus 0, minus 1 plus 1 on the C. So, and then I'm using the determinant. So this will not act to the determinant. So determinant of this matrix is equal to the determinant of this matrix because these row operations does not affect the determinant. Then here, I'm opening up with respect to this position. So this position is 1, this 1 is that 1. And the position is here is the first row, first column. This is the power of minus 1 factor is 1 plus 1. 1 is the number of the rows and plus the number of the columns. The row number is 1 and column number is 1. So 1 plus 1 represents the column number 1, row number 1, and column number 1. Then we are going to remove the first row, first column with our minds, and we will look at the minor of this. We call them minor 1, 1. Minor A1, 1 will give us this matrix, whatever is left here. That is A, 0, 1, 0, B, 0, and 0, 0, C. So that's coming from here to here. I'm using the matrix determinant formula. And this is 1, and the determinant of this matrix, since this is only the diagonal matrix, it's just a multiplications of the diagonal entries. That is A times B times C. This is a well-known fact. If you have a diagonal matrix, the determinant of the diagonal matrix, regardless of the dimension n by n, it's always the multiplications of the diagonals. I hope it is clear for you. Okay, that is that. And question 45. Use product rule of determinant to show that for a square orthogonal matrix Q, determinant of Q is either 1 or minus 1. So let's have a look what we are saying here. What was the orthogonal matrix? Let's remind ourselves what was orthogonal matrix is. Orthogonal matrix when the transpose of that matrix is equal to the inverse of that matrix. Now, what was the product rule of determinant? Product rule of determinant is determinant A, B is equal to determinant of A, determinant of B. Of course, when I'm talking about this one, n by n square matrices, right? As you know, we cannot multiply all matrices together. We multiply we can multiply only the certain matrices, and we are talking in the determinant concept related to the square matrices. So each of these square matrices, A and B, has to be a square matrix, and they have to be in the same dimension, such that this multiplication will make sense, and also the determinant will make sense. And another fact that we need to know is that we need to remind ourselves is that the determinant A transpose is equal to the determinant of A for every matrix, n by n matrix. This is the matrix, this is the n by n matrices over the real numbers, over the whatever your field that you're talking about. So this means for all. Okay, now these are the facts that we are going to use, and we would like to prove that determinant of Q is 1 minus 1, where Q is the orthogonal matrix. Let's use the orthogonality. Since Q is an orthogonal matrix, then we have the inverse and transpose are the same thing. So Q transpose Q, or Q trans, I mean other way around, right? That was the definition of, that way. So I have Q transpose Q, and the Q times Q transpose is the identity matrix. If it's whatever the dimension is, if n by n, that's n by n. So we have this equality. Now take the determinant on each of them. So we have the determinant of this, determinant of this, determinant of this. All of them are equal. But we know that determinant of identity, identity has ones on the diagonal. So the determinant of the identity is always 1. And this one is determinant of Q transpose Q, determinant of Q transpose. And now it is the time to apply the product rule. Then this will be the determinant of Q transpose, determinant of Q, using the product rule from here to here. Product rule for this one, determinant Q transpose. And this is just 1. So what we have now, it is time to use this fact, determinant of transpose is exactly itself. So here we have Q transpose is Q. So that is determinant of tet Q, determinant of Q square. This is what I'm doing here. So that is Q. It looks like a theta, but it should be Q here. The determinant, this is determinant of Q and determinant of Q. So the determinant of Q square is equal to 1. It means that this is the determinant of Q is the square root of 1, could be 1 or minus 1. That's all we need to prove. That's all we are required to prove for this question. I think that's enough to say. Okay. For question 48, now we have this determinant, and we would like to prove that this is equal to this quantity. And as you will guess, let's for a practical reason, let's call this matrix A. And we would like to apply some row operations such that we were going to simplify our calculations, determinant calculations. So we would like to make this one is 0, this one is 0. So row 2 is equal to row 2 minus row 1. Row 3 is equal to row 2 minus row 3 is equal to row 3 minus row 1. And these row operations do not act a determinant. So the determinant of A is this matrix after this row operation. So this is 0. So I'm doing the minus of this. So B minus A, B square minus A square. This is B square minus A square. This is 1 minus 1, 0. This is C minus A. That's C minus A. That's C square minus A square. That's C square minus A square. Now I'm going to open up with respect to this entry. So this is the first row, first column. This is why I have minus 1, 1 plus 1 here. And this 1 represents this 1. And the determinant of the minor A11, which is that little matrix here. So I need to calculate the determinant of this matrix now. So this is 1, this is 1. Only thing left is the determinant of this matrix. So I have this times this and minus this times this is the determinant of this matrix. So B minus A, C square minus A square, this one. And the opposite to diagonal has to be the negative side. We know that, I'm pretty sure. I don't think so you need to remind, but let me say. So if you have this matrix, its determinant will be AD minus BC, right? Do you remember that one? So on the diagonals, you have A times D, main diagonal, and the opposite diagonal will be minus the multiplications of the opposite diagonal. So that was the determinant 2 by 2 matrices. Okay, I hope this is, you know that one clearly by now. Now I need to arrange this polynomials so that I can get this simple versions of the solution. So that's what I'm going to do afterwards. So c square minus a square can be written as c minus a, c plus a, and b square minus a square can be written as b minus a, b plus a. That's what I've done from here to here. From here to here, I have a common factors. This is b minus a, c minus a are common on both sides. So I'm taking it up. What is left here, c plus a minus b minus a. So that's that guy. So this one and this one will cancel out. Only thing that is left here, c minus b. What I have, b minus a, c minus a, c minus b. I'm looking at what I want to find out is this value. Only thing that differs from this thing to this thing is just some minuses. So I'm turning this one by multiplying minus. I'm turning this one with multiplying by minus, and then I get this one. So basically, so minus one is plus one. So it does not, of course, I'm not changing the equality, of course, by doing this. Okay, so this one, we proved what we need to prove. That was the question 48. I hope these are all helpful for you. Thank you very much.